Basics first. What is RAM? RAM stands for random access memory. Think of RAM as your working desk. Imagine you're studying for exams. Your bookshelf contains 500 books, and your study table can only hold 5 books. The bookshelf represents your hard disk, that is the long-term storage, and the study table represents the RAM, that is temporary working space. You cannot work with all 500 books simultaneously because your desk is too small. Similarly, a computer cannot actively process more data than its available RAM without constantly moving the data back and forth from the hard disk, which is much slower. Why is the disk slow? So computers mainly use two kinds of storage. First is RAM, that is temporary, extremely fast, used while programs are running. And then we have the hard disk, that is SSD, permanent, much larger and slower than RAM. Approximate speeds, RAM around approximately tens of GBs, SSD a few GBs, varies by hardware. So traditional hard disk is much slower still. So because disks are slower than RAM, repeatedly reading and writing intermediate results can significantly increase the processing time, thereby slowing our processes. So we have basically single computer processing. On one computer, we have the CPU, RAM, and hard disk. All work happens here. Now imagine processing 10 terabytes of data. First question is, can 10 terabytes fit inside RAM? No. Second question, can one CPU process everything quickly? No. Third question, if the computer crashes, everything would stop. This approach doesn't scale well for very large data sets. So what does scaling mean? One of the most common interview words is scalability. So it is the ability of a system to continue performing well as the amount of work or data increases. Suppose a restaurant can serve 100 customers per day. Now suddenly 10,000 customers per day are coming in, right? Can they still serve everyone efficiently? If yes, the restaurant is scalable. If everything becomes slow, it isn't scalable. The same idea applies to software systems. Now we have vertical scaling. One solution is to buy a better computer. Suppose we have old PC with 8 GB RAM, upgrade it to 64 GB RAM. This is called vertical scaling, also called scaling up. So diagrammatically, it is represented as this: old computer to a better computer. We need more RAM and more CPU, more storage. Advantage is simple, no major software changes. Problem is, eventually you reach hardware limits. You can't keep adding memory or CPUs forever, and high-end machines become very expensive. Now we have horizontal scaling. Instead of buying one enormous computer, buy many normal computers. In example, instead of one computer, buy 100 computers. Each processes part of the work. This is called horizontal scaling or scaling out. Horizontally spreading. So you have now many workers performing the task for you, right? And this is an analogy. You can go through it. Now, what is parallel processing? So first we have sequential processing. That means tasks are completed one after another sequentially, right? Parallel processing is multiple tasks running at the same time. So this is happening parallelly. This significantly reduces total execution time when the work can be divided. Now, what is distributed computing? This is the one of the most important concepts in Spark. A large task is divided into many smaller tasks which are processed by multiple computers connected over a network. Now let's unpack every term in that definition. Task is basically a simple piece of work. Example, adding numbers, sorting data, filter records, or find averages. Divide is instead of giving one computer everything, we split the work, right? Now, network is where computers are able to communicate. A network is simply a collection of computers that can exchange data and messages. This could be inside a company's data center or in the cloud. Now, cluster is basically a group of computers connected together that work as if they were one large computer. The computers in a cluster are often called nodes. Each node has its own CPU, memory, and storage. Together, they cooperate to process massive data sets. Why not just use Python? You might wonder, can't I just use Python for everything? Python itself is an excellent programming language, but by default, it executes your code on a single machine. So we have this loop. This loop runs on one computer unless you use additional libraries or frameworks designed for distributed execution. Spark takes operations like filtering, uh, grouping, joining, and aggregating data and automatically distributes that work across many machines in a cluster. That's the key difference. Spark isn't replacing Python, it extends Python through PySpark. So your code can scale from thousands of rows to billions of rows across many computers. So this is the foundation for understanding Spark, right?